Hi everyone, my name is Hechuan Zhang. I'm a student from Xiamen University. It's my pleasure to present this project, Sensock 3D foot reconstruction with flexible sensors. Foot models have a wide range of applications, such as online footwear selection, clubfoot orthotics, foot morphology study, and gait analysis. Most of the existing methods of foot modeling are scanning by optical instruments. Laser scanner is widely known as an instrument with high precision. The disadvantage is that the instruments are expensive and the position constraint of cameras is strict. Some systems obtain a dynamic model by working on a glass platform with multiple optical devices. These systems are difficult to move and cannot be applied to non-experimental environments. For some low-cost equipment, such as 3D avatar feet, multi-image is mostly adopted. However, light, image background, and other unrelated factors will affect the accuracy of modeling. Sometimes the occlusion of the calf on the foot will cause a large deviation. Some researchers have tried using Kinect to scan foot by integrating available image capture technology, but the operation is very complicated and cannot be applied to dynamic measurement. So, how to improve the accuracy of the foot model and develop low-cost equipment is a widely considered problem. We've noticed electronic fabrics. It offers excellent levels of flexibility and malleability, and can be possible to mirror complex surfaces expandedly. Is it possible to design a wearable device to construct 3D foot models for non-professional users in non-lab environments? Based on this idea, we propose a novel prototype, Sensock, which is a solution to the task of 3D foot reconstruction in scenarios where users' comfort and long-term use are primary concerns. It is a normal sock with silk fibroin-based sensors. The sensors composed of PU yarn and silkworm fibers. The pointing PU yarns are helically wrapped by silkworm fibers with a wrapping machine. Next, the silk-wrapped PU yarn is immobilized vertically by two clamps. The silver nanowire dispersion is applied dropwise on the stretched elastic yarn. After this, the highly elastic and biocompatible material EcoFlex is coated on the yarns as the encapsulation layer. Because the silkworm fibers are wound around the PU yarns spirally, when we stretch the sensor, the change of the Poisson ratio causes the contact of the conductive fiber to change. The resistance value is changed accordingly. The manufacturing of sensors is complex, so we design an appropriate wiring location to reduce costs and prevent short-circuiting caused by contact sensors. In the manufacture of shoe lasts, some positions determine the comfort level of products. According to this, the final wiring network consists of 4 sensors determined by 2 protuberances of bone. These sensors are fixed to the fabric manually with a flat stitch to measure foot length, ball girth, instep girth, and heel girth separately. By using the scissor database, we extract the right foot and subdivided the model. That's the preparation. We calculate 4 girths of each shape in the homologous database. We use methods from other literature to design the triangular deformation matrix. Finally, we create a regression model by training the relationship between the matrix and the girth. This regression model could reconstruct the triangular mesh surface as the resulting shape with sensors reading inputs. To validate the property of Sensock, we design a comparison experiment. The participants are required to reconstruct their foot by using Sensock, 3D avatar feet, and Kinect. Here are some photographs of participants' right foot compared to the resulting shape. Depending on these shapes, we analyze the absolute error and calculate the mean absolute errors. For ball girth and instep girth values, Sensock is similar to 3D avatar feet and Kinect is higher. However, for foot length and heel girth values, Sensock reflects higher accuracy than other methods. We collect some comments from participants for a more comprehensive evaluation of Sensock. These comments are mostly positive. For example, Sensock is not different from wearing normal socks, and the expectation for Sensock as a VR device. But there are some negative comments such as the worry about hinging issues. Some people worried about damaging the sensors during use, and someone reported that Sensock was too small for their foot. These suggestions inspire us to perfect Sensock in future work. The current equipment has some limitations. Depending on the size of the sock, Sensock only supports size 36 to 42 feet. Participants whose foot shapes are significantly different from this range are expected to produce a larger reconstruction error. So, in the future, we will construct Sensock based on shoe last size information system, such as FSRS. This system classifies foot size with a number of size variations. To allow Sensock to support some additional applications, checking angle joints dynamically is necessary. Hence, we will design a dense sensor network. Some flexible sensors will be fixed to sock to cover the ankle. As we mentioned above, foot shapes have a wide range of applications. Here we put forward two potential applications of Sensock. The first one is to design and sell customized shoes. The service of customizing one's own shoes has already been offered by brands such as Nike, Converse, etc. However, most customers in the general population are not aware of their detailed foot metrics. Sensock offers a solution for non-professional users to acquire information about their foot shapes. With this kind of data available to them, customers could conveniently purchase their customized shape shoes online. Second is the treatment of hallux valgus, which is one of the most common deformities observed in foot surgery. In general, this disease is characterized by the adduction of the thumb. The most extensive treatment is the bending method of using orthopedic rehabilitation belts. However, the tension setting of the belt depends on the patient's sensation. Due to the lack of professional suggestions in terms of daily treatment, many patients also suffer from soft tissue injuries due to excessive tension in the belts. By placing a sensor on the deformed joint, Sensock could serve as a long-term monitoring device for valgus, allowing doctors to identify the degree of deformity and suggest the level of tension based on the patient's foot data. In summary, our work explores the use of stretch flexible sensors for reconstructing a three-dimensional foot. Furthermore, in comparison with other devices, we have found that Sensock has advantages in terms of reconstruction accuracy and user preference. That's all. Thanks for your attention.